This video contains the solutions to the triple integrals practice problems. For this first problem, we're just asked to evaluate this triple integral. So there's no need to change the order of integration because our function is 6xyz. That's going to be pretty easy to integrate. So we just get started in the order in which it's presented. So our first integral is with respect to y. So our outer two integrals stay the same. We integrate 6xyz with respect to y. That's going to give us 3xy squared z. And then we're going to plug in 0 and 1 for y and subtract. When we plug in 1 for y, we just get 3xz, and when we plug in 0 for y, we get 0. So this is just 3xz dx dz. Now we integrate with respect to x. That's going to give us 3/2 x squared z. And now we need to plug in -1 and 2 and subtract. When we plug in 2, we get 6, so 6z. And when we plug in -1, we get 1 for x squared, so that's 3/2 z. 6 minus 3/2 is 9/2. So now when we finally integrate with respect to z, we get 9/4 z squared, evaluated from -1, -3 to 1. So we plug in 1, that's going to give us 9/4. We plug in -3, that's going to give us 9/4 times 9. So that's going to be 9/4 minus 81/4, which is -72/4, which is -18. Now we're going to be given a region and asked to find the volume of that region bounded by those surfaces. So when we talk about finding the volume using triple integrals, what we're saying is that we're going to do a triple integral over that solid region D of the function 1 dv. So we could set this up as a double integral, but this is just meant to be a practice problem to help us figure out how to set things up as triple integrals. Now, because when we think about slicing this region vertically, in other words, from the z direction, the surface z equals sine y is going to be on the top, and the xy plane is going to be on the bottom, and that's consistent for the entire solid. We can see that from the picture. So that means that we can just slice with respect to z first. So we've got our double integral over our region R, and then we're going to integrate from the xy plane, which is z equals 0, to the surface, which is z equals sine of y. And again, we're integrating the function 1 dz, and then our double integral over R of the region R will be with respect to a, dA. So now what is R? So now we imagine flattening this region, this solid region, flattening it down, looking at it from the top down, and thinking about what our region would look like. So the way that the axes are oriented makes it easy to visualize in that way. So I would start by visualizing this with the x pointing down and the y pointing to the right, the way that it appears in our picture. And then we're going to reorient it the way that we normally look at these graphs in our next graph. So what do we have? So when we flatten this down, we've got our function y equals x here, and then it's going to be a triangle where this is the vertex 0, pi, this is the vertex pi, pi, and this would be our region R. So now when we reorient that in the normal way, with our y-axis pointing up and our x-axis pointing to the right, what we have is we just rotate that picture that we just drew counterclockwise 90 degrees. So we still have the graph y equals x, and we have this horizontal line here at y equals pi, and there is our region R. So setting that up as a double integral, again we can slice vertically. So if we think about slicing this vertically, the top of that slice is y equals pi, and the bottom of that slice is y equals x, and then x is going to go from 0 to pi. So that's going to be our double outer integral. We still have our innermost integral of our triple integral, and now we're integrating 1 dz dy dx. Now we, of course, have to do this integral. So we integrate with respect to z. That's going to give us z. The antiderivative of 1 is z, evaluated from 0 to sine y, dy dx. When we plug in sine y, we get sine y. When we plug in 0, we get 0. So this is the integral from 0 to pi, from x to pi, of sine of y dy dx. Let's finish this on the next slide. So now we do our next integral working from the inside out, the antiderivative of sine of y is negative cosine of y, evaluated from x to pi. When we plug in pi, we get negative cosine of pi minus the minus cosine of x. Cosine of pi is minus 1, so that's just 1 plus cosine x. Antiderivative of x is, antiderivative of 1 is x, antiderivative of cosine x is sine x. Plug in pi, plug in 0, and subtract. When we plug in pi, we get pi plus sine pi. When we plug in 0, we get 0 plus sine 0. Sine of 0 is 0, sine of pi is 0, so this just gives us pi. So now we have the function f of xyz equals 12xyz, and we want to find the average value of that function over the solid region that we see pictured here. Again, when we set up our triple integral, we would like to be able to set it up where we slice with respect to z first. So for that, we need to make sure that if we draw a line straight down through the region, no matter where that line is positioned, is that slice consistent? Is the top of the slice where the line first intersects the region always the same, and is the bottom of the line where the line exits the region, is that always the same surface on the top and the same surface on the bottom? And we see here that it is. The surface on the top is this plane 2x plus 3y plus 6z equals 12. Of course, we're going to need to solve that for z. So we get 6z equals 12 minus 2x minus 3y. Divided by 6, we get 2 minus 1/3 x minus 1/2 y. So that's my plane solved for z. So that's going to be the top of my line, and the bottom is just going to be the xy plane. So the innermost integral of my triple integral is going to be 2 minus 1/3 x minus 1/2 y. And again, we want the average value. So we're integrating the function 12xyz, first with respect to z, and now we're still going to be setting up a double integral over the region R that we'll describe in a second. And then we also need to divide by the volume of this solid region. We'll get to that a little bit later. Okay, so what's the region R? Well, again, if we collapse this region down, it's usually easier to draw a picture of the projection with the axes oriented in this strange way first, just because that matches up with the picture that we were given. So it's going to be a triangle. This vertex here is going to be 0, 4. This vertex here is going to be 6, 0. And the region is going to be this triangular region here. So in order for us to set up this integral, we're going to need to know what that line is. So using the points 0, 4 and 6, 0, it's not too hard to see that the equation of the line that we're looking for here is y equals negative 2/3 x plus 4. And again, if it makes it easier, we can redraw our picture with the x-axis pointing up, with the y-axis pointing up, and the x-axis pointing to the right, as we normally do. And so again, we see that the region has boundaries here where it goes to the point 0, 4, here where it goes to the point 6, 0, and again, it's this triangular region here. Now to set up our double integral, again, our inclination is to slice it vertically, which we can do here. So our double integral, this is the middle integral that I'm starting with here, the middle of my triple integral. The bottom of the slice is at y equals 0, the top of the slice is at y equals negative 2/3 x plus 4. And then the outermost integral, well, my minimum x value is 0, and my maximum x value is 6. So my outermost integral goes from 0 to 6. The innermost integral is still from 0 to 2 minus 1/3 x minus 1/2 y. We're still integrating 12xyz, and now our integral is dz, dy, dx. All right, what about the volume of this solid region? What's the volume of this shape? Well, that shape is a pyramid, and the volume of a pyramid is 1/3 times base times height, where the base is the area of the base and the height is, well, the height. So it's easy to see here that the height is 2. The base is a triangle, and the triangle has base 6 and height 4. So 1/2 base times height there is going to be 12. So the volume of that pyramid is 1/3 times 12 times 2, which is 8. And so the integral that gives me my average value of my function is this whole thing here, 1/8 times that triple integral. Now in this one we were only asked to set up the integral, not actually evaluate it, so at this point we're done. So now we have a solid region in our three-dimensional space, and we want to just practice setting up the integral in the various different orders of integration. So we don't have a function to integrate, we're just setting up a generic triple integral in all of the 6 possible orders of integration. So let's start with the easiest one, which would be slicing with respect to z first. So again, we imagine that we drop a line going straight down through some point of our region, and then we want to think about the top of that line and the bottom of that line. Those are going to give us our innermost bounds on our dz integral. Well, let's identify the different shapes here. So this top is the plane that they tell us, y equals negative z. We can tell it's a plane. This curved side is going to be our cylinder, x squared plus y squared equals 4. And then the bottom of the region is, of course, the xy plane, which is also known as z equals 0. So the top of this surface, the top of this solid, is y equals negative z, which we could also rewrite as z equals negative y. So negative y is the top, and z equals 0 is the bottom. And then we have our generic function f of x, y, z dz. But now we need to think about the region that we get by flattening this solid shape in the direction of z. So we collapse down to the xy plane, and as usual, we're going to think of this as the axes oriented more like they are currently, which is x pointing down and y pointing to the right. And when we do that, we're going to get a shape that looks a little bit something like this. We're going to get a curved shape like this with a boundary on the x-axis, and it's going to look like that. Okay, so what is this curve? Well, that curve is x squared plus y squared equals 4, right? If we look at this, the curved shape that collapsed down to give us that flat curve, there were no z's in that. So collapsing that down, getting rid of z doesn't change anything. So this is still the curve x squared plus y squared equals 4. And this is, of course, the x-axis, namely y equals 0. So when we reorient this in the normal way, with our y-axis pointing up and down and our x-axis pointing left and right, we see that the graph looks like this. So if this is x squared plus y squared equals 4, we can think of that as y equals negative the square root of 4 minus x squared. Negative because we're looking at the half of that circle that lies below the x-axis. So if we were going to slice this vertically, the bottom of the slice would be that curve, y equals negative the square root of 4 minus x squared. And the top of that curve would be y equals 0. And that would be our dy integral. And then x would go from negative 2 to 2. I can tell that because this circle has radius 2. X squared plus y squared equals 4 is the circle of radius 2. And so my x would go from negative 2 to 2, and that would be my dx. So that's one of our 6 orders of integration. Now, if I want to set it up in the order dz, dx, dy, a lot of that process is still the same. So I would still have my innermost integral be from 0 to negative y of my f of x, y, z, dz. And then all I would do is I would slice this region horizontally rather than vertically. So when I slice it horizontally, the top and bottom, quote unquote, of that slice are both on this circle x squared plus y squared equals 4. So I solve for x, and I get x equals positive the square root of 4 minus y squared. And then on the negative side, I get x equals negative the square root of 4 minus y squared. So those are the bounds on my dx integral, plus and minus the square root of 4 minus y squared. And then y goes from negative 2 up to 0. So those are the bounds on my dy integral, negative 2 to 0 dy. So those are 2 of my 6 answers that I want for this question. So to set it up in the other orders, I'm recreated in slightly crude fashion this picture. So now let's think about how we want to slice it first. So this was my x-axis, this is my y-axis, this is my z-axis. So now I want to think about slicing it with dy first. So now I think about drawing a line that's parallel to the y-axis that goes through my shape and out the other end. The top of the line is where it intersects the region first as it comes from the positive y-axis. So this is the top of my slice, which is the plane y equals negative z. And the bottom of my slice is on the other side, and that's going to be the cylinder x squared plus y squared equals 4. So solving that for y, I get y equals the square root of 4 minus x squared, the negative square root, because as before, we're in a situation where in the position in the three-dimensional space where y is negative. So our innermost integral goes from negative the square root of 4 minus x squared up to negative z. Those are the top and bottom of my slice with respect to y first. Now I want to collapse this down. So now I imagine flattening this shape in the y direction so that I just have the x-axis and the z-axis. And again, I'm going to draw an initial picture that matches as closely as I can with the way the picture that I have is drawn, and then I'm going to reorient it to be able to see it a little bit better. So what I'm going to see if I flatten this is I get a curved shape on the top, and that would be what my region would be. Okay, so what shape is that? Well, that's where the two surfaces, x squared plus y squared equals 4 and y equals minus z, intersect. And so if I make them intersect, then what I really get is instead of x squared plus y squared equals 4, since y equals negative z, I get x squared plus negative z squared equals 4. In other words, x squared plus z squared equals 4. And that's what that curve is. So if I reorient this in the normal way so that the x-axis points to the right and the z-axis points up, what I see is that this is just the top half of a circle. Z equals the square root of 4 minus x squared. So if I slice this vertically, the top of that slice is on the curve z equals the square root of 4 minus x squared, and the bottom of that slice is on the x-axis, which is where z equals 0. So my next integral, which is going to be a dz integral, tells me that z goes from 0 to the square root of 4 minus x squared. And then finally, x is going to go from negative 2 to 2, and that's my outermost integral, negative 2 to 2 dx. Now, if I want to integrate in the order dy, dx, dz, a lot of that is the same. The innermost integral is still the integral from 4 minus x squared, minus the square root of 4 minus x squared, to minus z. That hasn't changed. But now, what changes is when I've figured out my region, I slice it the other direction. So this top curve is x equals the square root of 4 minus x squared, 4 minus z squared. And this bottom part of my slice is x equals negative the square root of 4 minus z squared. So that's my next integral, from negative the square root of 4 minus z squared to positive the square root of 4 minus z squared. And now z goes from 0 at the bottom to 2 at the top. And so my last integral is from 0 to 2, and that's a dz integral. So that's 4 out of our 6 integrals taken care of. Now the last thing to do will be to slice this with respect to x first. So now if I draw a line through this solid that's parallel to the x-axis, it's going to intersect my solid like that. Again, the top of the line is where it hits the solid first, coming from the positive x-axis, and then the bottom is where it hits it on the other end. And again, what we can see is that this slice is going to be consistent. It's going to have the sort of top half of the cylinder on top and the bottom half of the cylinder on the bottom. All right, so the top half of the cylinder, so what is that? Well, we have to solve that for x. X equals plus or minus the square root of 4 minus y squared. And if the positive part is on the top, that's the upper bound, and the bottom half is the lower bound. So we have our generic function, f of x, y, z, and we're integrating with respect to x. Now we have to collapse this down in the x direction. So now we won't need two pictures, because now when I collapse down in the x direction, I actually get a picture that's like what I'm expecting to see. And hopefully you can see that when I smush that down, I just get this triangular shape. This right here is y equals negative z, which is a line. This is going to be a vertical line. That's going to be, this is the z-axis and this is the y-axis. So that's going to be y equals negative 2. Because again, that circle that we got has radius 2. So that's 2 units to the left. And so that allows me to set up my integral in both directions. If I slice vertically, that means I'm integrating with respect to z next. Z goes from z equals 0 at the bottom to z equals minus y on the top. And then lastly, dy, y goes from negative 2 up to 0. Negative 2 on the left to 0 on the right. Finally, if I want to set this up in the order dx, dy, dz, the innermost integral is the same. Negative the square root of 4 minus y squared to the square root of 4 minus y squared, f of x, y, z, dx. And now if I want to slice with respect to y next, that means I'm slicing horizontally. The bottom of that slice is at z equals -2. Sorry, y equals -2. I'm doing dy next. That's y equals -2. And the top of that slice is y equals -z. Finally, z goes from 0 to +2. This point here is the point -2, 2. So z goes from 0 to +2. And that's my final of the 6 different orders of integration.